Hello, welcome back to part 2 of Analyze Graphs of Polynomial Functions. Okay, we're going to get straight into some examples here. Sketch the graphs of these two functions here. Okay, so really quickest, easiest way to do this is just go through and look and figure out let's find out where all of our x-intercepts are at, right? So that we want to know when does this whole thing equal 0? So when does 0 equals x times x plus 4 times x minus 2? And really, again, as long as one of these three equals 0, we're set. So what makes this first part equal to 0? 0. What makes this equal to 0? Negative 4. And what makes this equal to 0? 2. So these are our x-intercepts at 0, negative 4, and 2. So we've got 0, negative 4, and 2. Okay, now the other thing you need to the only big other thing we got to do is figure out which way does this end up going. Okay, since this is a positive, since there's no negative out there, since this is positive, that means all the positive functions here are always going to end up going up. Okay, so a positive function ends up going up and a negative function ends up going down. So since this is positive, we know it's going to end up going this way. We also got to look, are there any double zeros or triple zeros or, to the fourth powers or anything like that? All these are to the first power, so all of these are going to cut. So it's going to cut through at 0, cut through at negative 4, and cut through at 2. Okay, so since this ends up going up, I know that my graph is going to end up going this direction. And then now all I'm going to do is just going to go backwards through this. So I know that all these are cut. So just somehow, again, a sketch just means roughly make it look okay. And since there's a bigger distance here, it's usually going to be a bigger loop. And that is a sketch. Sketch means roughly draw it. Draw it as close as you can. So if it looks like this and you got a little bump here and a little bump here, that's close enough. Okay, so that is a sketch of this function. All right, this function here, same idea. Let's figure out where all the zeros are at. So 0 equals this whole thing. In fact, we don't have to write that down because we just know that's what it's going to equal. So what makes this equal to 0? X-intercepts are going to be at negative 2 plus 2 is 0. Negative 1 plus 1 is 0. And positive 1 plus minus 1 is 0. So those are our three x-intercepts. So we got one at negative 2, we got one at negative 1, and we got one at positive 1. Okay, now where this is a negative function, so it ends up going down. So we know that it's going to end up going down this direction. Now we do want to know which one is the double 0, because we know this double 0, this means it's going to bounce. That's going to mean that means that this negative 1 is going to be the bounce 1, and then negative 2 and positive 1 are both going to cut. Okay, so we know if it ends up going down like this, so we just kind of guesstimate, and it's going to bounce off of negative 1. So I know it's going to come up here, and it's going to come down here, and it's going to bounce off of negative 1, and then it's going to cut through there. Okay, right? Because it's 1, 2, 3, fourth power, so we know it's going to end up, since it's negative, it's going to start by going down, and it's going to start as we go left to right. Sorry, as we're going left to right, it starts by going up, and it ends by going down. Okay, it's always going to end. The arrows are always going to be pointing the same direction on an even function, always opposite directions on an odd function. Okay. Okay, let's look at example 2 here. Write a cubic or quartic function with the least degree possible in intercept form for the given graph. Assume that a will be either 1 or negative 1. So we're just going to write the equation for each of these, right? So let's do, say, f of x equals, and we can start off by which direction does this end up going? Ends up going down, so it's going to be negative. And then we can simply figure out what the x-intercepts are, right? So that looks like that is at 3, and that looks like that is at negative 2, right? So we got, if we put a 3 in for x, what makes that equal to 0? Minus 3. And if we put negative 2 in for x, negative 2 plus 2 gives us 0, right? And this ends up bouncing off of this one here, so that means that this is a second power at -2, which is the -2 goes with the +2 there. So this is the second power, and that is our equation. That's all you really got to do for that is take a look at these and figure out the x-intercepts and figure out which way it ends up going, up or down, and away we go. So same idea over here. F of x equals, this ends up going down, so this one is also negative. And then let's come up with the x-intercepts. There's one at 2, and there's one at -1. So we put 2 in here for x. 2 minus 2 gives us 0. And put -1 in for the x. -1 plus 1 gives us 0. It bounces off this 2 here, so this one here has to be a square as well, and that is our function. Okay? Okay, we got one other example to go over, but before we do that, let's take a quick little comedy break.
Funny. Come on, Lola. Come. Okay, come here. You can do it. Come. Oh. Whoa, check out his teeth, guys.
Yeah, so he's on the fight.
You see the nose right there? Whoa! Jeez.
I told you.
Wow. Okay. Last example here. Sheena is creating an open top box from a piece of cardboard. She forms a square flap on the side, length x at each corner by making a single cut solid line and then folding the dashed line to form the flap. She then folds up the 4 sides of the box, glues the flap to the side it overlaps. What value of x to the nearest tenth maximizes the box's volume? So another way to look at this, because it's a little confusing here, is just think of, we're going to cut out this section right here, and we're going to cut out that, and cut out that, and cut out that, and then you're going to fold all these up and then tape it all up, and it makes a open top box. So if this is 8 and this is 11, starting with that, and then we got to cut out some lengths off the side here. What's the maximum volume that we can get for this? Okay, so volume of a rectangular prism is length times width times height. Okay, so again, if you think about folding these all up, let's call this, say here, the length. Let's call this here the width. Actually, better would be that this is the length, right, from here to here, and this is the width from here to here. And then this x here, this is going to be the height of the box, right? So that's going to be the height. Okay, so we know that the height is just going to be x. The length here, if you'll notice, it's not going to be just 11. It's going to be 11 minus these 2 x's, right? So the length is going to be 11, but we have to subtract off the 2 x's, right? So because it's just from here to here, so this whole thing is 11, subtract the x, subtract the other x, and that's going to leave us with the length. The width here is going to be, this whole thing is 8, but we got to subtract off the 2 x's for that too. So we can do 8 minus 2x for the width, and then the height here is simply just going to be x. So that's going to be the equation of our of the volume of this open top box. Okay, so now that we have the formula, what we're going to want to do is we're going to want to solve this thing. Now, it's not quite in the nice form that we've had before. I mean, it will give us the x-intercepts and stuff, but what we really want to know is we want to know the maximum. So we could multiply this all out and plug it in the quadratic and do this or that, or we can plug it into a graphing calculator. Now, TI-84, if you go to the links page, there's a graphing calculator help. If you click on that, take you to this page here. So you just want to go to bit.ly/stans TI-84. Hopefully this still works. I haven't checked it for a bit. It still works. So when you get this, you're just going to want to click on the blue box twice. Start, and then start. And then what's going to happen is it's going to give you the option of a couple different calculators up here. Right here, does most graphing? Nope, we want the TI-84, and what it's going to do is you will, on your computer, you will be able to have now a TI-84 plus. Oops, that's not what we wanted to do. We wanted it here. Okay, so you can use it. You can do everything we're going to do right here on this page here. I'm going to actually just use my actual same thing here. It's just an emulator. It just works a little faster on the online here. So all we're going to want to do is go into y equals, and then we're going to plug this in just like it looks. Okay. So it looks just like that, and just note that the X button is right here. It's down 1 and over 1, xt theta, and that's your variable button there. And then we can hit graph, and then cross our fingers that it looks nice. Okay, and here's what we get. So we can see that the graph goes way up here, comes way down, at minimums out there, and it goes back up. So we want to figure out what's going on up here. Right, so we got to find that maximum. Now, oftentimes you don't need to actually see the maximum, but it'll just kind of help out here a little bit. So what I'm going to do is push the window. We want to see much farther up. The lowest we see on the window is -10. We could probably do, like, say, -1, just so we can still see the graph. Maximum, we don't know exactly what. I'm going to put 100 in there because it looked like it went way up there. And then we can leave the rest, and then we just hit graph again, and then hopefully... Oops, we can see, still can't see more. Oops, I think I messed up I did the wrong window. I changed the wrong variable. That was the X. So we want to do, the X is fine at 0 or at -1, and then the max, we know it's not going to go past, say, 4, because half of 8 is 4, but we'll just leave it at 10. We wanted to change the Y. You can really leave that at -10, but it'll probably be a little nicer with -1. And then let's change that to 100. That's what we wanted it to do. Okay. So then we get this, and then there's our graph. Aha. And that's our maximum. That's what we're looking for right here. So what we want to do to find that is we do second trace, and that's calculate. So we're going to calculate what that maximum is. So we do second trace. We wait for it to go. Gives us this here. We want to find the maximum, so we can scroll down and hit 4, or you just hit the number 4 there. And now it's going to ask you left bound and right bound. So what you want to do is, we don't want to use these arrows. You always want to use the left and right. And right now we're at 4, so we want to come back. So eventually we're going to see, there's our cursor. We want to get that cursor to the left before it's hit the maximum. So we have to, on your calculator, you can just press and hold and it'll work. I have to tap it every time, otherwise it does weird stuff. So we just have to get that cursor so we know for sure it's before the maximum. So that's definitely before the maximum. So we just push enter, and then now it says right bound. So now we have to move it over using the left and right arrows, pretty much the right arrow. Move it over until now we know we are past the maximum. So there's the right bound, enter, and then I don't know why they say guess. It's like, yes, we want you to guess. They're actually going to calculate it. And then push enter, and it's going to actually tell us what this maximum point is. And there it is, 1.525 is the X, and that's at 60.01. So find the value of X to the nearest tenth that maximizes the box's volume. So 1.525, X equals 1.525. Volume is approximately 60 inches cubed, right? Because the Y is going to tell us what the volume is, right? So it's about 60. Okay? Okay. That's all we have for analyze graphs of polynomial functions. If you have any further questions on this, please feel free to ask in class. Thanks.